Welcome everybody. I'd like to give an introduction to linear programming in this short video today. And I'll be following the very nice notes, understanding and using linear programming by Matoušek and Gärtner. So first, just some comments on the name linear programming. Nowadays, when we say programming, we usually think of computer programming. That's not actually what programming means in linear programming. Programming is a military term, actually. So it's coming from how do you program the schedules for the military, or the supply lines, how you ship around the food, or how do you deploy your units. So this is back in the 1950s, I suspect, before computer science was all that, it was still growing. So people would argue that maybe a better name for linear programming might be planning with linear constraints. So we have a linear function that we're trying to optimize, linear constraints, and the programming term in linear programming is really more synonymous with planning than it is with programming in a computer sense. Of course, linear programming is closely related to computer programming because these algorithms that we'll learn about can be efficiently coded up. So let me give you one example. Linear programming came up in the time of World War II. So a lot of this was the US military was trying to, defeat USSR and vice versa. And so folks on both sides of the Iron Curtain were developing this. So this is an example coming from the Russian side. So I've simplified the graph, but the Russian mathematician Tolstoy was trying to figure out what's the most tons of concrete you can ship from St. Petersburg to Moscow in a day. So each label on an edge is a capacity in terms of tons of concrete. Okay, so each dot in this graph is a city, and each number on an edge is labeling the capacity of tons of concrete that you can flow in a day. So we want to get as much concrete from St. Petersburg to Moscow as we can. Any guesses how many tons of concrete do you think we can get, or upper bounds or lower bounds?
No more than 6.
No more than 6. I think that was Lander who said that. That's right. Yeah, Lander, you're totally right. No more than 6. Lander's realizing that because, out of St. Petersburg, you can only have 6 tons that leave any day. Or alternatively, into Moscow, you could only have 6 tons of concrete that come in. So what I've really drawn here is actually a cut. And there's a duality between max flow and min cut that maybe you've heard about. And that's a particular example of the duality of linear programming that we'll see later in this class. All right, let's try to realize a flow of 6 tons of concrete. So maybe I'll have 3 tons coming out of St. Petersburg along both paths. So the arrow is supposed to label the direction of the flow, and the number is supposed to indicate the amount. Okay. Leaving this next city right here, I can't have 4 tons leaving because I only have 3 coming in. Okay. So let's do the following. Why don't we put 2 of the tons coming in along the bottom route and the remaining 1 ton along this intermediate middle route. Okay. This city right here, we have 3 tons coming in. Why don't we have 2 going along the top route and 1 coming along the bottom? Okay. The flows along the top and the bottom, let's just keep progressing those sort of as far as I can. So let's keep going with 2 tons flowing along here, 2 tons flowing along there. Okay, let's see how, we might have to edit that, but let's see how we do. And let's keep 2 tons flowing along this bottom. Next, at this step, maybe I'm not going to do 2, because by the time I get here, I can only fit 1 ton of concrete. So with a little foresight, maybe I'll put 1 ton, 1 ton, and then I'll split this to have. Of the 2 tons coming into the city, I've split one going the lower route and one going the upper route. Okay. Into the city, we have 2 tons coming in so far. Why don't we just have all 2 tons going out? And then we'll have a flow of 0 along this edge, I think. So I won't even mark it a direction. All right, let's put a flow of 0 along this edge, and then focus on this city. I think right now we have 3 tons coming in. So let's have all 3 of those tons going out. And then finally, in my last step, I have 5 tons coming in. So let's get those 5 tons going out. And I've succeeded, right? Lander saw this obvious upper bound that I could never get more than 6 tons just by looking at what can leave St. Petersburg or come into Moscow. And now I've produced a flow that achieves that upper bound. You know, I in fact have 6 tons going from St. Petersburg to Moscow. There are other transport plans that you could come up with different than mine that would achieve 6 tons. But in this example, 6 tons is the most you can do. Questions so far?
So it seems like in this example, there is actually no necessarily optimal solution. Perhaps if you incorporated time into it, you'd find an optimal solution.
So I would say that there are optimal solutions.
Unique solution perhaps might be a better way to say it.
That's right. That's right. Here, the optimal solution is not unique.
Yeah.
Say what you mean regarding time. Like, Patrick, you said like maybe if you incorporated times.
Yeah. Well, so if you had time, because like say like this, I don't know, one path might be just inefficient, a zigzag path. You know, so it might take, you know, in this case where you're trying to do it efficiently, let's say, right, instead of zigzagging up and down, perhaps.
Yeah, here we've only looked at like the maximum amount of concrete we could flow, right? A different question would be, well, maybe you want to also move each ton of concrete over the least amount of distance as possible. Yeah. So you could refine your optimization problem, and then maybe you'd have a unique solution. Yeah. Cool. Okay, so this is like a quote unquote real world example. Let me try to just give you some intuition about how it would be related to linear programming. So let me change colors. You know, what we might do is we might assign names to each edge. So let's call, this is going to get a little messy. Well, how about I erase all the blue stuff? Okay. Let me just give names to some of the edges. So we have edge A, B, and C. For example, you could name all the edges. Okay. So each edge could have a variable corresponding to it. So XA would be equal to the number of tons of concrete transported along this edge. And then we have some bounds, right? So the capacity of this edge is 3, which means we get a bound that looks like -3 is at most XA, which is at most 3. All right. So, you know, XA could maybe vary from -3 to 3 in this example, because you could flow either way along that edge if you wanted to. So that's sort of, I would call this an edge bound. Okay, on this particular example, we'll also have vertex bounds. Let me show you an example vertex bound. I'll look at this vertex. All right. The flow coming into the city has to be equal to the flow leaving the city. Let's give a name to this city. Does anyone know another Russian city besides St. Petersburg or Moscow? Oh, come on. This is making me look bad on YouTube.
Stalingrad?
Stalingrad, thank you. Our geography is probably horribly wrong, Lander, but that's okay. All right, so let's look at Stalingrad. we don't want Stalingrad to like have more concrete coming in than leaves, because then over time Stalingrad is just going to get overwhelmed with concrete. Similarly, it's impossible for Stalingrad to have more concrete leaving than's coming in, because maybe Stalingrad doesn't have their own concrete factory. Okay, so what this vertex, I won't say bound, maybe I should say vertex equality would say is XA, the amount flowing into Stalingrad, has to equal XB plus XC. I guess I've written that in a biased way. I've written that in the biased way, sort of knowing that XA is what's coming in, and XB and XC are going to be the flows going out. So probably a better way to write this is, and then probably I need negative signs. Well, okay. Let me just do the following. I have to orient the edges. So after I orient the edges, then I've told you which way is negative and which way is positive. Okay. And the amount flowing in has to be equal to the amount flowing out. Probably a better way to write this is plus or minus XA, plus or minus XB, plus or minus XC is equal to 0. So anyways, I've started to describe how you might transport this into a linear program. We're trying to maximize something like XA plus XD. If I call that edge D, I'm trying to maximize the flow subject to some of these bounds. Other questions? Alrighty. We'll see in linear programming that in some sense there's no difference between the inequality bounds and the equality bounds, in the sense that you can turn one into the other, and both are useful. It's often to think about everything in terms of inequality bounds, and it's also sometimes useful to think about everything in terms of equality bounds. So we'll do that next week, but it's not hard to change every inequality bound into only equality bounds or vice versa. Let's go to a specific, more mathematical example. So I'm trying to leave the motivation from the real world behind for a moment and just do a particular mathematical example. Okay, here's our 2D plane. We have two variables, x1 and x2. We're going to try to maximize x1 plus x2 for all possible inputs, satisfying certain constraints. So let's draw these together. All right, the first constraint is that the x1 variable has to be positive. So I'll draw that as follows. The shading means that we're restricting ourselves to the right half of that line. Okay. x2 being non-negative, looks something like this. Right. We have this line, negative x1 plus x2 is at most 1. That looks something like this. All right. And x2 is bounded from below, so we should be beneath this line. And negative, x2 is bounded from above, so we should be up beneath that line. Negative x1 is bounded from below. Negative x1 is bounded from above, so we should also be to the right of that line. The line itself is, negative x1 plus x2 is equal to 1. And then all things below that line are less than or equal to 1. All right. x1 plus 6x2 is at most 15. That looks something like the following. And then finally, we have 4x1 minus x2 is at most 10. That looks something like this. So just some vocabulary. The objective function is what we're trying to maximize or minimize. Here, the objective function is x1 plus x2. We're trying to get as far in that direction as possible. The constraints are all of these. So I just drew all the constraints for you. You know, the feasible region is the region where all of the constraints are satisfied. So this right here in the interior is the feasible region. Right, those are the possible places where we could look for solutions. All right. The funny thing about linear programming is that sometimes to mathematicians, we just think it's trivial. Or how we might describe this to calculus students is this is a trivial problem, okay? And I think that's the wrong attitude. It makes it so that somebody like me can get to age 35 and not really know linear programming all that well. Okay, I just think it's trivial, when in fact it's far from trivial, and there's a lot of cool math hiding here. So why might a mathematician think this problem is trivial? Okay, I'm trying to maximize x1 plus x2. So I'm trying to walk, you know, as much as I can in that direction. All right, so let's just start walking, and I walk and I get here. And I can't continue in that same direction where I'm increasing x1 plus x2 as fast as possible, right? But I'm still not stuck. I can still like move this way, and I'm sort of continuing in that direction, okay? So I walk in that direction until I end up here. And now I try to walk in that direction and I can't proceed any further. So this is in fact our optimal solution. Okay, so ta-da, optimal solution. That's the perspective which linear programming is trivial, all right? But linear programming is much, much harder than that, as I'll explain in the next YouTube video, largely for the following reason, okay? So from these constraints, I just very like glibly and quickly drew for you our feasible region and all the vertices of the feasible region. It's actually hard to do that in practice. Algorithms exist, but they're slow algorithms. From the constraints, how do I find all these vertices? How do I find the feasible region? Algorithms exist, but they're slow. You know, I only showed you some of the possible linear constraints. Maybe there were many more linear constraints, like this one, or this one, or this one, or that one, that didn't affect my feasible region, but maybe they were part of the original problem. You know, how do you decide which are the constraints given to you that actually affect the feasible region, and which constraints are redundant? That's a hard problem in general. So we'll learn in this class about the simplex method. Okay, the simplex method proceeds as follows. You have to find some vertex of your feasible region, okay? That's hard. But once you do that, once you find one, let me color this a little bit more. Once you find one vertex, what you do is you find a path where you can walk along to another vertex in a way that improves the objective function. And then you walk to another vertex in a way that improves the objective function. And then you walk to another vertex in a way that improves the objective function until you reach a vertex where there's no neighboring vertex where the objective function can increase. Okay. In 2D, this picture is pretty in 2D, this picture is pretty misleading, because we traversed 1, 2, 3, 4 of the 5 vertices, okay? But you would imagine in higher dimensions, you might be only traversing a small number of the total number of vertices, okay? So you're not finding all of the vertices of this feasible region. You're only traversing a short segment. Questions so far? One picture I should draw while we're here is is these lines. Okay. So we're trying to optimize x1 plus x2. We're trying to optimize in this direction. If you look at those orthogonal lines, those are level sets of how well you've done on your optimization function. So this line, whoops, going through the origin, this line is x1 plus x2 is equal to 0. You know, this line right here, you know, might be x1 plus x2 is equal to 2. And then once you get up here, you get your optimal solution. This is where x1 plus x2 is equal to what? Okay, let's compute it. What are the coordinates of that point? This point has coordinates 3, 2. So at that step, 3 plus 2 is equal to 5. So, you know, that's the spot where we've reached x1 plus x2 is equal to 5.
So are the constraints always going to be half planes, or I guess half hyperplanes in higher dimensions?
Yes and no. So let me talk about this a little bit. So I haven't written a constraint like the following for you, Kyle. So I'm just drawing this example, but for the purpose of answering your question. I haven't given you any constraints that are equalities in this example, okay? In general, you're allowed both inequalities and equalities, okay, in your constraints. What we'll do, however, is we'll learn how to take a problem in the most general form, allowing inequalities and equalities, and we'll transform it into a very particular form. The form we'll transform it into actually will have, it'll have all variables non-negative, okay? And then every other constraint will actually be an equality, okay? So when we actually solve this using the simplex algorithm, we're gonna take these inequality constraints and change them into constraints of this form. To do so, we'll have to add in extra variables, as you'll see. So the way we'll do that a little bit is as follows. So, well, yeah, we'll see it when we get there. Are there questions?
Yeah, I've got a question, Henry.
Yeah, Lander.
Are there situations where, say, if this shape ended up being sort of not convex, that we could have a sort of end up starting the simplex algorithm at like a local maximum somehow, where the only paths to sort of adjacent vertices decrease the objective function, but you weren't at the actual optimal solution?
Oh, okay. Yes, good question. So the answer to that is no, and that takes math to prove. But okay, so in red we have the optimal solution, right? Lander's worried about the following situation. What if you start at a vertex, okay, and you want to start this simplex algorithm, and you ask, can I traverse to a nearby vertex that you know doesn't that improves the well, it doesn't make the objective function worse? Okay, the answer is no. So if you're at a space, if you're at a vertex where every other vertex makes the objective function worse, then that is guaranteed to be the global optimum, not only the local optimum. So linear programming is nice in the sense that you can't get stuck in local optimum. So in fact, if you start your simplex algorithm here and you see that every direction you try to move to nearby vertices makes the objective function worse, then you know you're at the global optimum and you don't need to leave. You're done. Now there's a subtlety in terms of that. And the subtlety happens when, so let's do the following. Let's, okay. I'm skipping ahead in my notes, but that's all right. Let's change our objective function. Okay, so we'll get back there. But okay. So what if I change our objective function? And let's now maximize 1/6 x1 plus x2. Yeah, perfect. Okay, so the direction vector has now changed, okay, that we're trying to optimize. Now it turns out that this entire edge is optimal, okay? So it'll turn out that an entire face can be optimal. Important for the simplex algorithm is when an entire face is optimal, there are still vertices that are optimal, okay? So whenever an entire face is optimal, there are still vertices that are optimal, these two vertices, okay? But we're finding the subtlety, oh boy, subtlety, adjacent vertices may have the same value of the optimization function. Okay. Here, these two vertices happen to have the same value of the optimization function, and they also happen to be global optima, okay? But you could have non-global optima vertices that just happen to have the same value of the objective function, okay? In those situations, it's not clear if you want to translate from vertex A to vertex B when they both have the same value of the objective function, right, Lander? And there are situations where you're at vertex A, all the other vertices are worse for the objective function, except there's a vertex B that's just as good but not better, okay? And sometimes from A, there's no place that you can go that's strictly better, but you'll have to go from vertex A to vertex B that's equal, no better than vertex A. But then from vertex B, you can keep going on to vertices that are strictly better. Do you see that?
Yeah, thank you.
Yeah, so I'll have to give you an example, with equations on Tuesday. So this leads to a subtlety in the simplex algorithm that's known as cycling, okay? So the naive simplex algorithm is simply start somewhere, find a better vertex, find a better vertex, find a better vertex. Every neighbor is strictly worse, you're done, okay? The subtleties come up when adjacent vertices can have the same value under the optimization function. And you could, if you're not careful in how you program this up, you could end up in a loop where maybe vertices A, B, C, and D all have the same value of the objective function, and you just loop A, B, C, D, A, B, C, D, A, B, C, D. When really, vertex E also has the same value of the objective function. You need to get out of this loop and go to vertex E, from which you can do strictly better and keep on going. Okay. We'll talk about that in detail. Other questions?
Henry, we asked them in the chat.
Oh my gosh, I've completely ignored the chat. Okay, Brittany, is that a convexity argument? I agree with Brittany. I think using the inequalities, it seems impossible to make a region that isn't convex. That is true. Yeah, okay, so you're totally right. When we're starting with these inequality constraints and we're these half spaces and we're taking intersections of half spaces, you always get a convex region. I won't even get into what convexity means right now, but we'll talk about that later. Brittany, what were you talking about regarding the convexity argument?
Our local maxes are going to end up being global maxes.
Yes, so that's a fact that's true in a more general setting. So we're in a linear setting for this class, but convex programming is more general. And in convex programming, whenever you have a convex feasible region, convex constraints, and you're optimizing a convex function, then every local extrema is also a global extrema. Yep, totally true. More questions? Alrighty. All right. So let me just start telling you the notation that is more broadly used for linear programming. We're trying to maximize C transpose X subject to AX is at most B. Okay. I'm leaving out the possibility of equality constraints in this. So let me tell you what C, capital A, and B are here, along with X. Okay. So X is our variables. Here we have two variables. So X is this vector, X1, X2. Okay. C in this example is the vector 1, 1. Okay. And then when we do C transpose X, we get 1, 1 times X1, X2. We're doing matrix multiplication. So we just get 1 times X1 plus 1 times X2. And that is indeed our function that we're trying to optimize. Okay. So the entries of vector C are just the coefficients here. There's a hidden 1 and a hidden 1. What is matrix A in this example? Matrix A is -1, 1, 1, 6, 4, -1. And I've just stolen those from the constraints. All right, so, you know, there's like a -1 hidden there. There's a 1 hidden there, a 1 and a 6, and a 4, and a -1. The highlighter's sort of fun. Okay. Great. So what happens when I multiply A times X? So I'm doing this multiplication, A times X. Okay, matrix multiplication. I'm assuming you're good with this, but let me know if not, and we'll chat sometime. You get -X1 plus X2 in the first row of your vector. You get X1 plus 6X2 in the second row. And you get 4X1 minus X2 in the third row of your vector. Okay. What is vector B in our example? Vector B is the coefficients on the right-hand side of these constraints. So vector B is 1, 15, and 10. All right. This less than equals to, in some sense, like, doesn't make sense, but you just have to interpret it correctly, okay? So if an undergrad linear algebra student wrote one vector is less than another vector, you know, that's -2 on the midterm, you know, because we're mean instructors. But what we mean when we say that this vector on the left is less than or equal to the one on the right is we mean that entry-wise, okay? So this first entry is at most 1, the second entry on the left is at most 15, and the third entry on the left is at most 10. And I'm not allowing equality constraints, you know, right now, but you might also write this in a form that allows equality constraints. So some variables have to be equal. Questions on that little conversion? Cool. I already discussed what happens if we change the objective function, you know, like this. We saw that instead of having a unique optimum solution, we had an entire line segment's worth of optimal. Let me briefly talk about these other possible changes. What if we reverse 2 of the inequalities? Okay, so let's clean clean up our canvas a little bit. All right, so what if we reverse, I'll just mark them, reverse that inequality and reverse this inequality, okay? So the shading is now gonna be on the opposite side. So when I shade on the opposite side, and then when I shade on this opposite side, my feasible region is now empty, okay? There are now no points in this domain that satisfy all those constraints. That's a possibility. Somebody gives you a linear programming problem and there's no solution. What's cool about the simplex algorithm is through the course of solving the simplex algorithm, you find that out. You learn, hey, you gave me a problem that had no solution, okay? The first time I show you the simplex algorithm, we're gonna assume that a solution exists, but that's just for simplicity. The most general simplex algorithm will determine if there's no feasible solution. All right, what if we remove the last two constraints? This last question here. So what if we got rid of these constraints? All right, so now it's like, this line's no longer there, and this line's no longer there. Okay. Now it turns out your function that you're trying to optimize, x1 plus x2, can get as large as you want, okay? You can just make this function larger and larger and larger and larger with no end in sight. When we first learn the simplex algorithm, we'll assume that that doesn't happen, that the optimal solution is bounded. But the fanciest version of the simplex algorithm will determine that for you. You'll actually find a one parameter of family of solutions that grows without bound in terms of the optimization function. Okay. So those situations are called infeasible problems, no solution, and unbounded problems when the optimization function can grow without bound. Okay, so what is the main point of this class? Linear programs are efficiently solvable both in practice and in theory. In practice, there's good software implemented in many different languages. You can have thousands of variables and thousands of constraints. And what you use here is you use something called the simplex method or the simplex algorithm. Linear programs are also efficiently solvable in theory. So in theory, there are algorithms which are, there are algorithms which are polynomially bounded in terms of the number of inputs. So they're polytime algorithms. So one such algorithm is the ellipse algorithm. This runs in polynomial time, which is considered fast from a computational complexity perspective. The simplex method, in the worst case, runs in exponential time, which is considered slow from a theoretical perspective. So there's a tension. The algorithms that are good for bullet 1 are not the same as the algorithms that are good for bullet 2, okay? In practice, the simplex method is very fast, okay? Theoretically, in the worst case, it's slow. In theory, there are algorithms that are polynomial fast, that are considered quite fast in theory. In practice, those algorithms are not really used. It's a simplex algorithm that's used. So we'll talk about this interplay between theory and practice. It really drives a lot of innovation in the subject. The theoretical algorithms have led to new, faster developments for the practical algorithms. Questions about that? All right. Let me end this video just by briefly surveying the significance and history of linear programming. So there was, a computer science journal that published an article where they tried to pick the 10 most important algorithms of the entire 20th century from 1900 to 2000. And that's when computer science was invented. So the 10 most algorithms that are important ever, okay? And Simplex algorithm was chosen as one of them. You could debate that fact, but it's debatably one of the top 10 most important algorithms ever. It is largely, it's developed by George Dantzig. He was working for the US Air Force, developed around 1947. A lot of this work was top secret until it was later published. As the Americans and Europeans were developing such tools, the Russians and the USSR were doing the same thing. So Kantorovich considered some versions of linear programming as far back as the 1930s for organizing the timber industry in Russia. It's important enough that folks have gotten the Nobel Prize for it. Kantorovich and Koopmans in 1975, Nobel Prize in Economics. Dantzig never got the Nobel Prize for this, whereas perhaps he should have. Perhaps Kantorovich as well. When it came out, entrepreneurs, businessmen were very surprised when their costs were suddenly cut by up to 20%. They had a way of flowing concrete from St. Petersburg to Moscow, and they just sort of did it by hand, what looked the best. And somebody came along and cut their costs by 20% overnight. The Simplex algorithm is feasible on large problems. That's as much due to advancement in the algorithms as it is due to advancements in computer hardware. Okay, so maybe you've heard of Moore's law. Computer hardware debatably gets faster by a factor of 2 every so often. That's not what sped up linear programming the most. The most has been the development of algorithms, which is what we'll talk about in this class. The duality theorem in linear programming is quite important. It shows up not only in linear optimization, but also convex optimization. Convex optimization, there's a duality gap sometime. Here, we're in the simpler setting where there's no duality gap. Linear programming is now considered like easy, but many nonlinear problems or convex problems are based off of linear algorithms or use linear algorithms in an iterative fashion. All right, so with that, I'll end. Thank you all for your time and attention.